The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Yes, sir. Go ahead.
Well, good afternoon to one and all. I'm Shastri Vedula. I've chosen to talk on this topic because it has been one of the ideas that has been at the deepest level worrying me for quite some time. In most of the engineering colleges, you see that the facilities are all practically 50 years and down the lane, and these facilities have never gone through any improvisation or inputting or putting in the latest trends and changes that are happening in and around us. That's the reason why this thought came to me, and I put it across to the management of this college. This is called Gayatri Visakhapatnam College of Engineering. When I came back to India very recently, about a couple of years ago, and once they agreed in principle to some of the ideas here, then I try to look for the best approaches followed within the country and outside the country. In the process, I saw something good that has already happened at IIT Madras, and so I looked at it and I said, well, this is the best approach that one can think of in trying to say what should be the type of electrical machines and drives lab like, and not just that it should be a totally integrated kind of approach wherein we teach courses in modules, but we never put them together in any format such that people can understand the whole of it, not the part of it. So with that kind of background, you can see that many of the ideas here are derived out of that. And this facility has been in operation over here for the last 1.5 years. We first started using this facility for our graduate students to start with, because we want to know whether they can manage and understand and assimilate the ideas here. And you can right up front, let me put it this way, some of the concepts that we felt are meaningful are today the time of everybody, both the students and the faculty, and the lab space is very important. So we need to use the time of the students very efficiently, and so is the lab space. And especially with increased real estate costs, you can see that this is enormous. So, and most importantly, the other thing that you also see in any of the experimentation in the good old labs is when you teach a topic on a module, you can't experiment on some other module, or either in time ahead or time, mostly in time ahead. So that's creating a lot of problems. So by this kind of facility that we are going to demonstrate or show it to you rather, of course demonstration is out of question, they can experiment on anything at the point where you are teaching the course to the students. More time of the students can be put in for the analysis and writing, and also report writing, because you spend less time in carrying the meters, connecting the wires, or blowing up. I mean, I'm not saying connecting the wires is a bad approach, but at the same time, you would see that every time you don't have to redo the whole thing, and they should know that the circuit is right, and then they know how to make the connections, and you don't have to carry meters and then return and then spend more time there. And that's the part where the students are, in my opinion, losing a lot of time. And most importantly, with the energy costs going up, the lab by itself should be energy efficient than a traditional lab. So you can't afford to have 5 kilowatts, 10 kilowatts, 20 kilowatt machines and then try to operate them a good number of times. So that energy efficiency is also important. And it's also space optimized. That means generally we put all the meters, etc., in a horizontal form. Instead of that, wherever there is a space constraint, you go vertically upwards. You would see the same thing happening in this lab. And the other thing that you see is most of the instrumentation is all analog type. everybody has now moved from analog to digital. You see that happening in every branch of engineering or electrical engineering per se. And consequently, we went in for this digital instrumentation, exposure to virtual instruments. And then by this, you can get the dynamic behavior of electrical machines, not just both the transient and dynamic, and not just the steady state part only, which is what every time most of the people as teachers we will be spending time on. And in other words, we can see the dynamics part in the lab concurrently when things are happening. This is exactly what we call it, real-time monitoring of parameters or diagnostics and things of that nature can be done. So let's look at now what this lab is all about. What are the components in this lab? That's exactly what this overview of the test bench components is all about. This is the front panel of a typical workbench. It is a workbench consisting of number of motors, and in the back plane you have about 4 motors which are tied together and onto the same shaft, and consequently those four machines, I'll call it. It could be a motor or a generator. There will be 2 DC machines, 1 induction motor, and 1 synchronous machine. So all these, because most of the subjects that you teach from one level to another level, they are all deal with that. That is one aspect of it. And all the machine terminals are brought, as you can see here, machine terminals are all brought here. And we also have load terminals brought here. And then the switches to connect and disconnect this power supply. Then you have the isolators whenever you want to disconnect the power supply to them. And then, as usual, when students can blow up things, you need to have protection. And so you have fuses, circuit breakers, supply terminals are also brought here. And as I said, we are also talking about virtual instruments, not just classical instruments, which are digital in nature. Like you can see, most of these displays here are all digital meters that you can see here. But right now, this is not active demonstration, but a passive demonstration. We also have embedded around the same workbench a DC motor drive and an AC motor drive. And you have also an auto transformer by which you can also input the variable frequency, not variable frequency, variable voltage, but constant frequency type of input. So that is the front end of this workbench. Then here are this is the back plane of all the 8 workbenches. This is the one that I'm talking about. There will be 4 machines which are connected onto the same shaft. This is the induction motor. You have a DC machine, and the other side also you have a DC machine and an alternator. And this is an electromagnetic coupling. So in other words, if you don't want to operate all the 4 machines together, you can disconnect. Making use of the electromagnetic clutch, you can disconnect other 2. So that's how you can bring in energy efficiency. Well, you can see a bit more of whatever I said in terms of the magnetic clutch. And then you also have a blocking rod, especially if you want to operate, let's say, an induction machine and conduct a block rotor test. You need to block the machine such that it doesn't rotate. So that is the purpose of this blocking rod. Then you have you can see this is workbench 2 and this is workbench 1. And then on the same way, you can see that onto the extreme left, you will also see 2 workbenches. And then behind this, you have a replica of the same thing. So altogether, there are 8 workbenches. And in addition to rotary machines, you can also have transformers as it is shown over here. Well, the other thing that you can see is the typical power supplies that one has in this lab. You have 3-phase AC power supplies in dual mode, that's one or the other you can use. And then the same thing is true, because in terms of reliability, even if one, for some reasons, if some power supplies are not working, the other one should be up and running. That's the idea of it. You have isolators and you have fuses built into that. That is the kind of power supply. That means, and most importantly here, the DC power supply, you don't need a separate DC power supply to be derived from a batteries or rectifier. Instead, this DC power supply is derived right away from a reduced 3-phase AC, such that you get 220 volts DC over here. Most of the 3-phase ACs are obviously the standard 415 volts 3-phase 50 Hz supplies. And this is a typical auto transformer, but this is specific in the sense it is isolated. It's not a non-isolated type that normally people looking for, especially if you want to do power electronics centered experimentation. There you need to have this kind of isolated windings, but in the form of an auto transformer. That's why you have this kind of auto transformer. Then this is the electromagnetic clutch that you see here, that what you show here, that can be connected, energized or disconnected, and this is primarily meant from the point of view of speed sensing. And this is the blocking rod in a closer view, and this is the same thing in a different, probably it's a deep replica of the previous thing that you saw. And then most importantly, many of these components are not are imported. They're all locally available here. You can see many of, and the components and the company that that has supplied these components. And then you can see all the mission terminals are brought onto the same panel. You can see DC motor 1, 2, the armature side, and then the field side. And similarly, similarly for the AC motor side, it's an induction motor, obviously, when you say AC motor, and the 3 terminals which could be connected in star or delta. Then you have obviously AC generator. You have the 3-phase terminals. All the 6 terminals are brought out, and you have the field winding part here in terms of F1 and F2. Well, the load bank that is required, and as I mentioned, that we also have these motor drives because this lab is just not meant for a undergraduate education, but also meant for graduate students, that is our MTech students. So we integrate this along with the other part. That is how the drives component, the classical machines operation, and then integration of the drives with not just the machines or the drives, but the whole equipment that you have in that workbench can be what should I say, can be instrumented in such a way that you can have virtual instruments, and then you can have also digital instrumentation, putting all this together such that you can have the information stored, and then so that you can retrieve it anytime you want, or you can repeat that experiment without much loss of time. So that's how so in other words, that is the emphasis of integration. Integration means you should have all the machines at one single place, including the drives. You should have virtual instruments. You should have the means. For example, you will see how the voltage measurement is done with the these are basically digital voltmeters, and as you can see there. And most of the times you can see these sensors to which the BNC connectors are connected. They are all Hall-based sensors, so that you can measure the voltage through this BNC connector connected back to the DAQ, that is data acquisition system, which in turn will be connected to a PC in which typically LABVIEW would be residing, and with the corresponding drivers for the DAQ. Okay, so basically this is on the voltage measurement part. You can see the voltage ranges are basically plus minus 10 volts, and these BNC connectors we can see later on how this will get connected to the DAQ terminals. This is on the current measurement part, on the same lines as that of what we said in relation to the voltage part. Then power measurement, then the corresponding selector switches, BNC connectors. That is, these are these BNC connectors from the point of view of measuring the power part. And of course here any given power is limited to like 1.5 kilowatts, because we have about how many 8 beds and 4 machines, all to the 32 machines. They could be running at the same time all the time. So we need to limit the peak power rating within that lab, and hence each machine is limited to something like 1 kilowatt. So then the RPM measurement. Now this is the other thing that I mentioned, changing over to digital instrumentation from analog metering. So that is the important focus in this lab. And as I said, not only we go in for digital instrumentation in terms of display, that's like a backup, but we also have virtual instrumentation. That means like VIs derived from LABVIEW and DAQ, integrated into this whole setup. You'll be having, obviously, I think I will show you very soon that there will be a computer on the desktop along with a monitor and a keyboard, so that you could do the programming part of it and extract the information or that you really need. That's the instrumentation part. Here is the concept of what we really mean by digital instrumentation or virtual instruments. These are, you can say this is a load component. You can measure current or voltage, take it through a transducer like a heart probe kind of thing. Then that gets, of course, you do the signal conditioning part of it, take it through the MyDAQ, and that gets connected to the PC with the LABVIEW software, from National Instruments. Well, these are the digital voltage sensors. You can see they are within the range. Most of the voltages shall be calibrated within the 0 to 10 volts, whether it is voltage, AC voltage, or a DC voltage. And same thing could be said of current transducers. For a three-phase, there will be 3 terminals. Then you can see all the 3 currents, and also the DC side voltages can be measured. And then the digital wattmeter measurement. In fact, you may ask, why should we have also digital? But you can multiplex the measurement that you are doing, and then calculate that power measurement as well, or you can directly get this through these transducers. Well, this is the kind of computer that I said, which is also integrated with each workbench. And you can see here, this is a typical mini-size desktop, and this is the monitor that you see there. And the back side of that, you have the hard disk or the PC. And then here is the DAQ that you can see here. We removed the terminal, and then you can see the logo of National Instruments as a part of the DAQ. And of course, the PCs are not set up from a local company. So that's the kind of thing that you have. So the type of DAQ that is chosen is DAQ 6341 from National Instruments. By this, what you are really doing is you can sense the voltages, currents, or speed, or whatever, retrieve, get all the information back onto this DAQ, and from the DAQ you can you can have the front panel and write the block diagram, and then try to extract information in real time, and even display it concurrently, and even plot. I'll show you some basic experiments that we did it at the undergraduate level as well as at the graduate level. Of course, this work is just not that of mine. Let me assure you, this is the work done by many of the faculty right over here in the last, I would say, 2.5 years or 3 years. Some of the good faculty who worked on this project, they have gone for greener pastures, like PhDs admissions, because they got PhD admissions elsewhere, like in IITs or in other countries. Well, now these are the DAQ panels in a closer view, and you have 15 analog inputs and then 2 analog outputs. And look, this is the data acquisition in the integrated missions lab. What are the steps involved? In fact, we give short courses to the students in and around this Visakhapatnam in Andhra Pradesh. This gives you a snapshot of what this data acquisition is all about in the shortest time that is at my disposal. What this contains, basically the ideas here are that you look for a specific NI DAQ which has analog inputs, analog outputs, and digital outputs also. And when you have these digital outputs, you can use them for triggering devices which you may have in power electronic equipment and things of that nature, if you program it properly. And or you can also get the speed measurement and measure that, or you feed these digital inputs after with a proper device driver, trigger a MOSFET or an IGBT and so on and so forth. So these are the basic things that you require in terms of configuring the DAQ, adding the DAQ to the VI, and then building a VI in a LABVIEW software. Basically, it's a virtual instrumentation for engineering workbench. That's the acronym, and the whole thing today is everybody calls it as LABVIEW. This is how a typical DAQ, what we are using in this lab, looks like. This is the latest at the time when we purchased it, and these are all single-ended type. Of course, you can also configure them as 8 differential mode, and you have those analog inputs, 2 analog output channels, and 24 digital channels as well. Of course, this BNC panel or connectors will give you the option to plug and play kind of thing. And this is exactly the closer view of it. Last time we saw it as a part of the workbench. Now this is a close-up view of all these BNC connectors. When you want to connect these sensors centered outputs that come here, they will get connected to the DAQ. That wiring is already well. Sorry, because of a power interruption over here. Whenever power goes, I don't know, even the network is down for some reasons. So I hope it's not too much of a distraction, but it has given us to think power quality is as important as anything else that we want to really do. especially in the internet-based time frame in which we live. Hello? Hello?
Yes, sir. Audio is coming, sir.
Next, you can see. Yeah, is it audible, right? Good.
Yes, sir.
Yeah, can I proceed?
Yes, sir.
Good. Thank you. Thank you. Well, these are the BNC terminals for connecting these terminals to the DAQs that one has, which goes with the computer. So, in other words, today we have these electrical machines. You have the drives, and we have all the power supplies that we are interested in, and the protection that is required in a given lab. And we have the computers. So what is missing is there is nothing that is missing except bringing in all of them together and then try to show to the students that this kind of integrated approach helps the students understand things better, because here you can do work on instrumentation, power measurement, or you can work on dynamics of the electrical machines, not just only the steady state characteristics of the machines, and so on and so forth. Now let's quickly let me take you through this whole thing. I think my monitor is not moving. I think I have a problem here. What is the slide number? Okay. Well, we are now coming to this data acquisition part. This I have already explained. Okay, good. This is the specification of the DAQ. I think I didn't cover this portion of it before this power supply break. And these are the typical specifications. If you go onto any website and then put that number, then you get all these specifications. Typically, what is it that we are using here? And then programming the DAQ is equally important. Without that, you can't establish a communication between the sensors and the DAQ and from the DAQ to the computer. So there are 4 discrete steps that are identified. You have to create a new VI in the LABVIEW according to this step. Add a DAQ assistant block to the block diagram, and there is a procedure for this. I'm not interested in teaching you how to connect a DAQ to the computer, but you can find these kind of things coming up once you have the equipment with you. And the other thing is configuring the DAQ terminals. That means which are the terminals that you are trying to connect to the DAQ from the given machine. It could be some 2 voltage terminals and 1 current, or all the 3 voltage terminals and all the 3 currents, etc. And even if you want to make power measurement also, you can do that. It all depends on, of course, the maximum number is limited to something like 13, while 2 of them are meant for a spare. And the last point is, once you get all this data, if you want to analyze it and then display it, you need to do this kind of make use of this signal-based palettes, or whether you combine the signals or even separate the signals such that you could view them, or split the signals such that you can could see that through this block diagram. And from the block diagram, you can see we can see, for example, how this teaching and learning goes through making use of this LABVIEW and data acquisition with specific lab experiments, which many of my colleagues are now using it to demonstrate this to our students. I'm talking about students at the 4th semester level and 5th semester level. Not just only our MTech students, but also the undergraduate students, of course, of the EEE branch to start with. Well, this is we start with very simple examples, then we take you to higher levels of advancement, or higher levels of how we can use this to other problems or other investigations. Many of the concepts are, basically this is how do we teach the concept of phase or a phase difference and power factor using the software called LABVIEW. And this is a specific circuit that that the student builds, and once he builds, and then you can sense the, for example, the current and then the voltage and also the power. And once you do that, you can display them. So this is how you can. This is how the so-called results look like in the view graph that you can see here. This is a typical the active power component. This you can see the voltage, which is probably the blue, and the red is basically the current, and that is a phase difference between these two. And the phase angle is also mentioned here. There's a typical inductor, and this is the power factor of the circuit. The fundamental frequency, and well, the THD is very small, but if your power supplies are corrupted, sometimes you do see some small little kicks like this. So this is a typical RL circuit based power measurement and display. And let's take the second example, that is magnetic saturation in a transformer on no load. This is a typical. Normally saturation is maximum when the transformer is on no load, when you keep increasing the voltage applied to the primary or secondary of the transformer. So this is a typical schematic which everybody knows, and you do the circuit, again take this, so corresponding current, it goes to the corresponding banana connector, and similarly you can make the wattmeter connections here. There is a corresponding probe BNC connector. From there it can be taken to the DAQ and then to the LABVIEW residing in the PC. Well, this is how the block diagram looks like. This is the DAQ assistant. Here the signals are, this is like a, here the three signals are split into these components, and some voltage signals are multiplied by 80, current signals are multiplied by 2.5. You can also do some harmonic spectrum, waveform. These are all waveform. Graph means you can display the graph, you're making use of that, and you can detect the fundamental. If you want to determine the THD, you can also do that. So all that is, and then if this were to be some kind of a well, it depends on what you want to measure. This is typically, as I said, for a transformer. So in a transformer, what we are looking for is basically saturation, and the saturation means there could be a dominant third harmonic. That's exactly what we are trying to see here. So this is the voltage waveform, and that's the red one. The white waveform is the current. You can see the peaky current that you can see, and most importantly, the phase shift is 90 degrees. And through this harmonic spectrum, you can see the fundamental and also dominant third harmonic. So all that is displayed here. So in most of the conventional transformer experiments, you hardly talk about this. We don't talk about harmonics at all, though we know under which saturation there will be a dominant third harmonic. So this is exactly what is being displayed and conveyed visually and through this virtual instruments. Well, the next thing is like take the case of a DC generator and the magnetization characteristic. Normally we talk about this. This is like getting the open circuit characteristic, seeing the saturation there. But there we don't talk about saturation, but saturation is a asset in the sense the self-excitation helps, and consequently this is a typical experimentation that we can talk about it. Is a open circuit characteristic, self-excited DC shunt generator. That's exactly based on some resistance in the field circuit, and then here once it self-excites, you can connect the load. That's this, and then self-excitation obviously pops up from the remnant field that one has in the DC machine. So the two DC machines that one has can be used here. One as a generator, the other one as a motor. Motor starts to rotate this, and this gives you the. But if you want to, or you rotate the generator, allow it to self-excite, and then connect it to the load. Well, this is the typical block diagram. As I said, we run short courses to explain to the students, or to ensure that the students will have the capabilities to build their own block diagrams. Most of the times, initially we provide this kind of block diagrams to the students. Afterwards, they build on their own and then come to the class with the necessary preparation to build the block diagrams, and then continue with their work. And this is how the sample front panel looks like. That's the block diagram. This is the front panel output. This is the typical open circuit characteristic. This is the field circuit line, and this is the operating point that you can see. And then from this same block diagram, one has this critical speed and critical resistance values that one can calculate as well concurrently. So in other words, calculations are done much faster, but thinking and writing the report takes time. That's where the students can spend more time and most efficiently. And you can stop all these DAQ operations by clicking on this DAQ stop. That's the so. And then the last in the series at the undergraduate level is what is the way one can do electronic synchronization of the alternator with the AC mains. Normally we do it physically through a dot lamp approach. Instead of that, we went in for the approach of using the virtual instruments and then make use of the Boolean knobs to ensure that if and when certain conditions are satisfied, well, you can close the switch. That is the so-called thing that is isolating the generator from the bus or the power supplies. So this is basically the counterpart of dot lamp synchronization, which we have been doing for 50 years. But here it is done through an electronic synchronization, through the Boolean part and the graphical indicators in the LABVIEW, as you can see in the next slide. Okay, but this is the classical ways of operating the given generator from the point of view of synchronization. It will be driven by a motor. Then you get the three-phase power supply, and here is the isolator. If and when certain conditions are satisfied, then you can see that this switch will be closed. And so you look for the instant, that is, instead of the, you can let me take you through other part of it. This is the block diagram for the whole thing, and you can see here if the difference in the two voltages from the generator to the bus is 0, as it happens here. These are the so-called Boolean controls in the LABVIEW, and then obviously if and when you see that these are glowing and then that this voltage is 0, then you close the switch. So that is the so-called electronic synchronization that is a part of this LABVIEW centered lab bench that goes with the synchronization of the alternator with the mains. So we don't need to worry about the so-called the light of the bulbs getting onto our eyes. Instead, you can see a eye-friendly monitor, and then the so-called the typical signals that you can see from this differential knobs there. And in case there is a phase mismatch, then obviously you can see that these voltages are not equal, and you can see these are glowing. That means this is not the time that you can synchronize it. So there is a need for the phase sequence to be identical, both from the generator side as well as from the system side or the grid side, and the voltage difference should be small. Then only you can synchronize it. All that is displayed from this. Well, when you do all that, you can also come up with some graphs, that is the so-called V curve and the inverted V curve for a given synchronous motor. So that's exactly what you see. Well, let me see how much more time we are left with. I think I may have another 10-15 minutes. I will now take you through slightly to a higher level where the graduate students will be working. So far, what are the achievements that we have we have gone through? So you can see improving the effectiveness in learning. That's basically digital instrumentation, computers for using that, and then the LabVIEW centered activity for data acquisition. And we can see, and by this, we are not having 8 oscilloscopes at all places. We are not having power supplies to these oscilloscopes. All that is gone. And most importantly, I will call this, this is a student-centered approach, hopefully leading to effective participation of the students. And also you can call this as active learning, because if he doesn't get it right, he has to learn and debug the program and ensure that the program works. That is the, these are the achieved advantages that are achievable advantages. Well, we have been so far talking about undergraduate students and the space around how this lab space can be used, but now we want to go to a higher level, that is like a graduate level activities. What is it that we could do further? Because as you can see, this whole lab is built on, in the concept, according to the concept of modularity. And obviously, it helps to reuse the premises at graduate level or even for research activity. Initially, and for quite some time, many of our graduate students have used this, and then because we are not sure whether the undergraduate students can assimilate this kind of concept, because this kind of lab space was used in IITs, and here is a kind of good engineering college in Vizag premises. And of course, it's quite popular amidst the local people, local colleges over here. So you can see the power quality measurement that can be done using the DAQ. We have demonstrated this without having any power electronic equipment per se, as in the case of a transformer. We can also do modeling and simulation, because LabVIEW has also got the what you can call as tools to write models in math language or MathCAD equivalent language. And once you build the model and then identify the whole model in a graphical plane, you can use that and then try to see how the models work and what the models would convey even before you start to experiment and acquire the data, such that such information that is so acquired can be compared with the simulation data. So that means by this process you are really validating the models as well. So that is the advantage. And what is more, we also have this industry standard DC and AC motor drives, and these are the most general drives that one sees when a student goes to industry. This classical DC motor drive is nothing but it's a single quadrant drive for the DC motor, and the AC motor is nothing but again simple VBF controlled motor drives. By this, even though the motors are small, the generators are small, if you want to maintain the speed constant and ensure that you can operate this without the need for a large flywheel or a moment of inertia, you can help achieve those objectives. Well, this is a typical power quality thing that one can see here using virtual instrumentation. Okay, this is the typical thing that you can see how the block diagram looks like, starting with DAQ, and then this is a frequency measurement channel, RMS voltage, power level, and then frequencies. You can measure the THD both for the current as well as for the voltage, and you can measure also the current RMS as well. Well, this is a typical small. It's basically just to demonstrate this concept. We have used this as a diode rectifier bridge connected in a single phase to an R&R load, and you can see the current drawn from the source is almost like a rectangular wave. While this is the source current. Well, the fundamental current component, if you extract the fundamental component out of that, will be this, and this is the harmonic spectrum out of that. So you can see the THD value is almost like 40% in the source current. That's how you can get this. And we also did modeling and simulation as a part of this using LabVIEW and Multisim. Multisim is primarily used from the point of view of power electronic circuits. This has large similarity to that of the PSPICE kind of simulation. So you don't have to really go to the essence of both having LabVIEW as well as Multisim is that you could do mathematical models in LabVIEW and you could do circuit-based simulations in Multisim, and then you can put them together to operate such that they can coexist and you can have a co-simulation approach. That's exactly what we do. So for example, inverters, choppers, etc. you can do simulation, or even interleaved choppers and things of that nature, or basically these machine models like induction motor, DC motor, or a synchronous machine model or BLDC motor. You can build the models in LabVIEW, and then you can now put them together and ensure whether you're and in fact many of the digital controllers can also be built under LabVIEW. That's a sense of it. And well, that is the other advantage that we get in this kind of integrated approach, wherein you have a computer, a monitor, and you have the data acquisition, and the kind of experimentation that you really want to do in addition to modeling and simulation. Okay, this is a good old way. Initially, we started doing this before we got this whole equipment to understand how this whole thing would work. You need to have a regulated power supply, a transducer, then a MIDAC and a PC. So if for the existing equipment you want to do it in a simple way, we can do it like the prototype. This is basically a prototype concept that we built before we got this equipment from Rockwell Automation. And this is a way that was integrated, though it looks, you see, somewhat like a prototype, but we have been able to integrate this with the existing equipment that one has, which is somewhat dated. Okay, that's typically the induction motor with the loading, and then you are using the data acquisition to acquire the data from that. Well, this is the same thing in another way. This is typical experiments. So the load test on this induction motor, especially calculation of the efficiencies and like what you see here, or this or even the slip, it should be somewhere here. The speed, once you get speed, you can also calculate the slip, and you can. So in other words, you can build the even steady state models like equivalent circuit model, and then calculate the efficiency characteristics, etc., for a given load test on a given induction motor. When you do that, then you can see here, this is the kind of course here we didn't want to direct online start this motor, so we increase the voltage initially such that the acceleration, the speed voltage is increased properly such that the current is within some specified limits, making use of obviously the auto transformer. And in the process, you can calculate the speed here, then the phase voltage, phase currents, and the slip here. Of course, because this is operating on no load, the efficiency is practically zero. So that's how you can do both this dynamic and dynamical data as well as static data you can acquire and then plot. And this is a typical model for a synchronous generator. And just to give you that, you can start from the primitive level like power measurement to that of building a seventh order synchronous machine model using the same LABVIEW. LABVIEW, everybody thinks is meant for only data acquisition only, but that's not true. LABVIEW can be used also for other applications like modeling and simulation. That's the other thing that we have learned after getting this software and using it. And of course, this is the other way of now we have operated these drives with the motors that we have, and the only thing is these are all modular. We don't have to use at the graduate level. You don't have to use it at the undergraduate level. They will be operated, and then they will look into the characteristics of these drives, which if they are connected to the machines. Well, this is the so-called Integrated Machines and Drives Lab at Gayatri Vidya Parishad College of Engineering, and the summary is this is obviously a 21st century lab with modern equipment, not just the software but also the hardware. We just don't acquire just data as everybody thinks that LabVIEW is meant for that. We also use that for modeling and simulation. So in this integrated approach, what we have looked, basically the broad area of most of the electromechanical devices, that means all machines, drive systems, and their control has been implemented. Well, that's it. And thanks for your hearing. Thanks for your time. If there are any questions, I don't know how we can, probably you can send it in the form of a, now I'll pass it on to Mr. Srihari so that he can see what needs to be done. I don't know how much more time we are left with. We are practically done. We have got another 5 minutes probably time. So I'm done with my presentation part or webinar part. Well, it's now open to questions, or if you can.
What is the price of each test bench?
Well, it's a good question. Price comes from quality. Quality costs. That's all I will say. And if I don't want to openly talk about the price, but you can send me an email if you are serious about it. But uh, what I mean, I don't want to talk about costs in public because, but it costs us a fortune. To an extent, we spend about 100 lakhs just for the machines lab alone, and another 45 lakhs for the LabVIEW software. But this is all the LabVIEW software is for the campus-wide licenses, and the outcome of this is everybody now in this college has started to use, not just in this department, but in other departments as well. For example, the other day, mechanical engineering department faculty and the graduate students started to come and use this, mainly from the point of view of making vibration measurements. The ECE people have been using it for demonstrating things in their own way. In other words, LabVIEW becomes a tool for effective teaching and learning. That's the way I put it. But this is the, as I said, well, we could have done with one setup. We didn't want to do it that way. If we have to make an impact with all the 8 batches working concurrently on the same type of workbench, same type of experiment, we wanted to have it this way. And the management was very proud, came forward, and we built it. Next question, please.
What is the Rockwell automation in this project?
They did the total integration, and the ideas are primarily from the academicians, and the LabVIEW software was purchased by us. The integration is all done by us, because I know the next question would be, what is your role? So that's the reason why I want to tell you that upfront. So Rockwell, basically, we wanted to have that industry outlook. You can see the whole thing is it's like an industry product, because reliability is most important if you want to deal with day-to-day conducting experiments for all these people. Because if anything goes wrong, then we can't upset the whole timetable. So reliability is most important. So, and prototype, as I said, we did build a prototype. We know what the concepts are, but we can't have that kind of equipment in the day-to-day run-of-the-mill type of experimentation, which the undergraduates have to go through, and that is the reason why we have. And most importantly, Rockwell has done this for the first time when IIT Madras wanted to explore this concept, because their intake has been doubled, the space remains the same, and consequently they have to reshape the whole lab. And I happen to know that place because I have been there myself for more than 3 decades, and consequently that has strengthened the thought process that I have put into the management here, and they readily see, once you say it is done in IITs, well, others will catch up. That's exactly, and most importantly, if somebody from that place tells yes, we can do it, this is exactly what we did. Yes, we can, and we did it.
Instead of Rockwell machine, will it be possible to use existing machines at colleges and NI software and hardware?
It can be done. Yes, it can be done. It all depends on how much time you want to spend. I'm not, basically, as I said, Rockwell has, I mean, the reason is this. We, the academicians, we think we can replicate what the industry people can do, and the converse. It doesn't really happen because you don't have the time. Most of the times you hardly get time to do your teaching and also doing a little bit of research. And when do you get time to do the prototyping? So it has to be done outside, but with your ideas. And there should be dedicated workforce to do that. Then it can be done. It's not impossible to do it. In fact, as I said, we did build it in our own way. That prototype thing that you can saw, that I said that dated. Basically, we used the old equipment and we made use of that, and we came up with this result. So understanding can be done, but you can't make a product in an academic environment and which works 24/7.
To what extent can we use MyDAQ for power quality monitoring?
Yeah, well, we have demonstrated the whole thing. It can be done. And what accuracy? Well, we have verified this thing through simulation, and consequently, the accuracy depends on your DAQ and the samples you take, and the program. Mostly in terms of how well one can write the software code in terms of the block diagram.
This idea of lab is the government going to do or support in any other city?
Well, I didn't understand. Any other city means? Well, we can see. We have been giving workshops to the people in and around Vizag. We have done that, not just to. Of course, primarily we concentrated it on the colleges in and around Vizag. It did attract good number of students, but after some point in time, we are also not getting much time. But it can be done at other places. But ideally, I would say if there is somebody who has a good idea, he can write a letter to me, then we can discuss it further.
Would you be interested to travel and conduct workshop at Chennai, Hyderabad, Bangalore, etc.? This is Mr. Visweswaran from NI.
Oh, well, Mr. Visweswaran, you know how much I travel, but I don't travel too much. If there is a need and purpose, we can do it. It's not a problem.
So those are all the questions, sir. Thank you very much. Just now I'll send you the recording in a few minutes.
Very good. Thank you. I hope you relished it, because you did not see this whole thing in this kind of operation, if I'm right, though we gave you some glimpse of what we did about 1.5 years ago.
Yes, sir.